Good afternoon, everybody. Thank you for attending the session. We will have 4 presentations, and so we'll ask that you ask all of your questions at the very end. Our first presenter is Dr. Halls, and Dr. Halls is a professor of geography in the Department of Earth and Ocean Sciences at UNC Wilmington, studying spatial patterns in barrier islands, tidal creeks, land use, wildlife movement, and recently human health versus environmental conditions.
Thanks for coming, everybody. It's hard to do the first talk after lunch on a beautiful day. There's probably a few people on the beach right now. So welcome to our session, and thank you all for coming, and thanks to the people on Zoom. So this presentation this afternoon is a culmination and a continuing effort that students in my lab at UNCW have been working on for many years. And what I want to talk about today is sort of where we're at in this project of studying barrier islands. And so the co-authors on this presentation are several of the students who have worked with me studying barrier islands and how they are changing through time. So to preface this project, we've generally over the years thought of barrier islands moving and changing through time and how we study them from 2 different perspectives. The first is studying the land cover or the habitat and how that habitat can change through time. And the other perspective is studying the geomorphology of the island. Sort of these 2 different ways of thinking about islands and how they can change through time. And so through the history of this project, were those 2 different perspectives. And now we're putting those 2 ideas together into one geospatial model. And through the power of ArcGIS Pro and merging these 2 ideas together and having that model all working at the same time, it's now a better model. And so that's what I want to talk about today is this merging of these 2 models and the idea of using imagery and LiDAR to help us make a better model of barrier islands. Okay. Can everybody hear me okay? Okay, thank you. So to give you a little refresher on the importance of barrier islands, they are the first line of defense along our coast. They protect the coast from flooding and erosion. They provide a wider range of habitats for lots of different species and of course biodiversity. They provide recreation opportunities and economic prosperity for our coastal environments, our coastal region. And because of this environment, they are dynamically changing suddenly from storms, but also they change slowly through time, such as a change in sea level. And to put that into perspective, across North Carolina, we have over 7,500 miles of wetlands just along the shoreline. That's a lot of miles. And so these barrier islands are an important part of our coastline. And so understanding how these places are changing and putting that into perspective of the population change along this rapidly changing coast is also an important reason for studying how these barrier islands are changing. Oops, sorry. Along North Carolina's coast, though, besides the 7,500 miles, there are 2 main coastal systems at work. The northern coastal zone, we think of the Outer Banks. These barrier islands are much flatter. They have a lower tidal range, which means they have fewer inlets. The islands are longer and they are further from the mainland. So those islands are different than the southern coastal zone, where these islands are in a steeper condition. They have a higher tidal range. The inlets means that they have more inlets, and these barrier islands are shorter in length and they are closer to the mainland. So we should not think of the North Carolina coast as all being the same types of barrier islands. They are very different in the northern coastal zone from the southern coastal zone. Also, our coastal zone has a changing sea level. As you can see in this slide, the changing sea level varies from the northern coastal zone, which has, and I apologize, you cannot see, there we go. You can see the legend on this map. The yellow arrows have a higher changing sea level than here we have down in Wilmington, which is a lower changing sea level. So the amount of sea level, rising sea level is much more rapid in the northern part of the coast than it is down here in Wilmington. So the conditions are not all equal across the state. So what is the morphology of a barrier island? We might think of these islands, like where we are right here in Carolina Beach, as sort of a ubiquitous kind of place, and it isn't. The habitats vary across the island. So the habitat types from the back barrier have these intertidal wetlands. Think of these as the salt marshes, and they vary from Spartina intertidal wetland up to a supratidal habitat, which is that very top of the tidal range, up into upland scrub habitats, all the way to upland grass, all the way to the ocean front. And then from a morphological standpoint, we have different sea levels on the ocean front, the dunes, we have channels, dunes, swales are these valleys behind dunes, these other hummocky, topographically high areas. And then we have behind there, these overwash fans are very important because those are indicators of where there have been breaches and sand has made it from the ocean front to the back barrier. So it is this combination that we are really trying to study between a changing habitat, which are these changing habitat land cover types, and this changing morphology like channels, dunes, swales, hummocks, and overwash that we are trying to model simultaneously. Does that make sense to everybody? There's a habitat characteristic and a morphology characteristic that we're trying to model. So we're doing this with two types of data. The first is WorldView 2 satellite imagery and LiDAR. So our goals with this project is to, one, create a single ArcGIS Pro model that will automatically derive land cover and geomorphology. Automatically. You put in the data, you put in all the parameters for that data, and it outputs the land cover, and it outputs the geomorphology for your barrier island. It will automatically compute the accuracy assessment. It will automatically compute amount of change through time, and it will automatically publish all the data up into ArcGIS Online. This is a little different than a traditional land cover mapping approach, right? That usually it takes many, many months of people. Yeah, you're all nodding like, yeah, this is a little different approach. And you can imagine this has taken many years for us to figure out the best approach to do this in an automated way. So in a very short number of minutes, I'm going to try to summarize how we've tried to pull this off. Sorry, I'm not doing very well with the slide advancing technology. There we go. So we've tested this at a number of islands throughout North Carolina, some developed and some undeveloped. And what I'm going to talk about today is at Masonboro National Estuarine Research Reserve, right off the coast of Wilmington. It's an undeveloped barrier island. And as I mentioned earlier, the southern part of North Carolina's coast generally has shorter barrier islands than up in the northern part of the coast. But actually for this region, it's a pretty long island. It's bounded on the north by a rock jetty. I don't know if you can see my mouse, but there's a jetty here at the north to protect this inlet. It was constructed in 1981, so there is a little bit of human influence on the north end. And down here at the southern end is an inlet that gets maintained all the time because of the need for fishermen to come in and out of Snow's Cut, which is also an artificial Corps of Engineers cut, right? So that's the island that we've been studying. The workflow in general, and I'm not quite sure how well you can see all of the words on this workflow diagram, but in a nutshell, there's always field work involved in a good land cover and geomorphology study. And so numerous field efforts have been involved to collect RTK GPS points. Those GPS RTK points, you can see the number of them here, are randomly selected in half to train the model. The second part of the workflow is to compute a maximum likelihood classification to do the initial land cover classification. The third component over here with the LiDAR data is to derive DEM and DSM data and a variety of spatial metrics that I'm going to talk about to derive the initial geomorphology model. And you'll see down below there is the initial land cover maps and the initial geomorphology maps. And the reason they're called initial is because after that is when we mash them together to derive the best from both of those to come up with the refined data that comes up with the best approach to redefining and pulling out the best of both of these to come up with best forest classification, best super tidal classifications, and all of these habitat types that are now better because we are using both data sets together in the model to produce the best output possible from both worlds, either the remote sensing world or the GIS world, to define the best habitat maps possible and the best geomorphology maps possible. And ultimately, I'm going to talk a little bit more at length of how we do this, but ultimately the model comes back with the final geomorphology maps and the final land cover maps. We compute the accuracy assessment, and then we compute change through time. And in this case, we have dates from 2010, 2014, 2016, and 2019. Here's an example of the data points for all the RTK work that's done on the island. And you can see an example zoomed in of all the data points that are collected. And these are, again, randomly selected for training the model. And then the other half are used for computing the accuracy assessment. The data that goes into this model has to be, of course, pre-processed. So to just give you a little bit of background of what has to happen to the data before it goes into the model and what kind of knowledge does it have to have for the model to run. First, the imagery has to be atmospherically corrected. The LiDAR data has to get corrected for the correct tidal datum. And this is in NAVD 88. You have to pull in the values for the most accurate tides at the time that the data are collected for mean sea level, mean high or high water, and highest astronomical tide for each date and time that the imagery is collected. And again, these are the dates that we had for the data. Because of course, this is a tidal environment, right? So it's really important that you know what the tide environment was for the data that you have. And we used these tidal environments, mean sea level, mean higher high water, and higher astronomical tide to define these elevation zones for the different habitat types and for using the morphology model as well to define supertidal from intertidal, et cetera. In the geomorphology classification, here are some of the highlights. For example, the intertidal class was any elevation that was greater than mean sea level and less than mean high or high water. The supertidal is defined this way, etc. So you can see how these are somewhat easy rules to implement in a GIS. Once you've corrected the LiDAR data for your tidal regime, you can implement that in a model. Some of the other things we've implemented are things that are still spatial, but are a little tougher to implement, even though they're a spatial concept, like A channel we defined as a depression because it looks like this, right? It's a channel. They are cut by water, so that's an adjacency sort of thing. So once you've defined water, a channel should be adjacent to water, and it's generally perpendicular to the beach. Perpendicular is tough, right? As a GIS person, that's sort of a tough concept. There's no tool that says, hey, I'm perpendicular. So that's a little tough to figure out. Swales we defined as are also depressions. They're generally behind a dune, and they also, like according to how we define them, do not intersect with a supertidal area. So it helped us to figure out how to reclassify things and say, whoa, they shouldn't be this class, they should be a different class, right? So these are all ways for us to work through the model and correct things and get them into their right class. And dunes and hummocks if you remember our little schematic of what a barrier island looks like, dunes and hummocks are topographically are very similar to each other, but they're slightly different shapes. And so dunes and hummocks have the similar topography, but their shape is different. So dunes are elongated and hummocks are more circular. So a couple of equations that we implemented, the TPI is a topographic position index. Anybody in here use the TPI before? It's a super cool index. I urge you to investigate it. It essentially helps you define hills and valleys. And if you ever have any need for anything related to topography where you want to identify places that are more on the apex of a hill or a trough, the TPI is what you want to look for. And most TPI uses happen in really hilly areas, like think of the Piedmont or Appalachia. Very rarely has it been done in the coastal plain where it's super flat. So you have to really work with it to figure out what those parameters need to be in a very gently flat area like Wilmington. But it worked. So this is a TPI equation if you're interested. And we also use the shape index to help with these things that are circular versus more elongated. Have other people ever used the shape index for things? Yeah. Yes, right. Some trees, are very circular. And also, if you want to separate like parks that are very, might have the same signature, it's very green, but a park is usually a very regular shaped square looking thing versus a natural area, it might be more circular. So shape index is a really useful equation to implement in a GIS. Excellent. So we implemented those in the model to help us refine and improve the results, not only just for the geomorphology, but they also did help a little bit also on the land cover classification as well. Okay. So here's what the land cover classification model in a nutshell looks like. We did use the NDVI, and this is all in Pro, right? This is not a separate package. Everything was all built in Pro. It's all parameterized. You just have to, put in the data and hit run, and it runs and outputs, and all the data comes out. We ran the maximum likelihood classification for all the initial land cover. And then again, like I said, all the output was then refined based on the results of both data sets. Here's more input of the further refinement of land cover. I just want to prove to you that I did do it. And then here's the geomorphology classification and how it runs through everything. And then it gets finally to the change analysis. Is it just me or is it slow? And then we get some results. So you can see that all the models worked pretty well. The weakest one was 2010 geomorphology. And this is very, very normal that your oldest date is your weakest date, right? Because your most recent accuracy data, the ground reference points come from now. So going back in time, it's typical that those are the weakest dates, right? Because they're the older dates. Anything with a kappa coefficient technically over 0.4 is acceptable, although I would say it's still kind of weak. Compared to our earlier work that we did with an earlier model that did not combine the two together, these are all an improvement, so yay, but you know, there's still room for improvement. If people were to ask me what I would do better right now is and we are doing it, is we would divide the island up into their separate units of where the island is different. The island's a big island, and the north end is different than the middle, is different than the south. I would process it in those chunks and you would get a better result. Come on there, mouse. This is a lot to take in, but basically these are the amount of area of each class and the amount of accuracy. The highlight here is that, you know, the accuracies are pretty good and they were an improvement over our last model or sets of models through time. Don't you hate it when people put up slides you can't read? There's been a lot of change through time and a lot of swap through time. One of the things to highlight is at different, and you can go to our website. We've produced a website for you to look at that. What we've seen happening is a lot of the marsh grass has become super tidal. So it's matured, right? And it's doing really well. We've had hurricanes during this time period and it's helped the marsh grass. That's a good thing, right? Because marshes love to have sediment accumulate them on them from the front side of the dune going to the back side, and the marshes grow. So they've done really well. What does that mean? On the ocean side, the oceans have retreated. The front side has retreated at various places along the dunes. That's essentially what's happened. That's what's supposed to happen. Here's a summary of what I was just talking about, where you can see the gains in emergent marsh. That's the same as salt marsh. So in blue, we've seen more marsh happen, and in red is where it has eroded. Such a delay. In the geomorphology, the most change has been in red. There you can see that there was a loss in overwash. That means that things have changed, and some gains in overwash. So I will point out right here that these overwash fans expanded right here, and that's where the dune broke through during a storm and it gained in overwash fans. And you can really see the channels broke through, everything broke through during the storm event and created an overwash fan. And when it says loss of overwash fans, that means the grasses all grew on top of the sand. And it's really cool to see in the map. So I urge you to go to our website. If I run out of time, I will show you the URL for this. Are we almost out of time? Okay. So what have we learned? The implementation of two mapping models, land cover and geomorphology, into one model improves the results of both. Having enough ground reference points is always a challenge. We did not have enough for some of those classes. There was almost no forest cover on Masonboro Island, right? I don't know if you guys have been to Masonboro, but maritime forest is very hard to find. There's very little of it. So having enough ground reference points for some of those smaller habitat classes makes it a really difficult class to map. Leveraging the power of data automation improves these workflows. I urge you all to do that. Based on these dates, the largest storm events did have the biggest impacts on the island. Again, mapping coastal wetlands isn't easy. Intertidal salt marshes are generally large swaths of low-lying vegetation. They are tidal areas, and therefore accurately mapping them depends on when the imagery is captured. I can't emphasize that enough. So if you grab imagery that was all collected at high tide, you will not be able to map them very well. So even though we're getting imagery all the time, if it's all at high tide, it will be very hard to map that. Okay, super tidal marsh this is one of the things that we talk about all the time in my lab and with other people around the country. Supertidal marsh is generally always lumped into intertidal marsh because it's one of the most difficult categories of marsh to map. And it's also one of the most important because it's that line between upland and intertidal. And it is that indicator of how sea level is changing. But it's just a little ribbon. So from a geographer's perspective, like from the bird's eye view looking down, you can hardly see it. But when you're out on the ground, you can really see it. So it's a challenge. It's one of those classes that will probably always be difficult to map. The accuracy will probably always be low, but it's important because it's that indicator of how sea level is changing, and it's that indicator of how the habitat is changing. So I'm a proponent of keeping that class. We've thought about ideas like there's this program called CoastSnap. I don't know if you guys have heard of CoastSnap. It's a super cool program where on piers and different places around the coast, they're mounting hardened mounting brackets where anybody with a smartphone, you can mount your smartphone and take a picture, and it automatically uploads and the software will automatically document changes through time. I want to do that at this little ribbon of supertidal marsh because that's the only way we're going to be able to document it because it's such a little ribbon. We're not going to be able to see it from space very well. So I'm trying to put in like the plug to get one of those things on Masonboro and anywhere else anybody wants to put one of these stands. So if you've never heard of CoastSnap, it's a really cool project and a friend of mine is involved with it and it's very cool. Here's our website. I'm happy to share this link or you can go Google it and I'll send it to you. It has all the data on here, does all the information about this. I'm happy to share all the results and the data with anybody who wants it. And yeah, there it is right there. It describes everything. There's a whole interactive, all the maps, you can turn all the maps on and off and zoom in and zoom out and see how the land cover is changing. There's a little bit of a delay, so I don't know if we have time for me to show it all to you. There's the overwash fans. Okay. What's the online question? So the question was, have you tested drone imagery to get better results, essentially? We have tested drones on Masonboro and drone imagery, and we added LiDAR to the drone also with Dr. Procope. If anybody saw Dr. Procope's talk earlier this morning, we had a grant with DOT to test a LiDAR drone and captured multispectral imagery as well. It was awesome. Mapped wetlands like beautifully. The pro is you can go out and you can collect that data. It's fantastic resolution. Yes, you can map the habitat types. Geomorphology, haven't tested that yet. The con is it's a massive amount of data. Massive. It would not run in this model. Okay, it's a massive amount of data. And you could not collect the whole island in one trip. Right? We collected, one little area and it took all day. So it would take many, many trips to collect the whole island using LiDAR on a drone. Yes. Repeat the question. What kind of hyperspectral imagery? Many more bands. Right. That's a great question. So the question was, have we tested with hyperspectral? And in this model, we have not tested with hyperspectral. That's a great idea. We just wanted to get the model running with this type of imagery first to make sure the model would run. It's a great idea. I would love to do that. And I would love to talk to you about how to implement that idea. I think it's a great idea. The trick is, here's my caveat. I want to do it all in one software package at a push of a button. I want to make the model easy to run. Yeah, and you're right. There's always a catch. Yeah, I know. Exactly. I'd love to talk to you more about it.